From this lecture onwards, we will be talking about complex numbers. Well, not only complex numbers, but in particular, we will talk about functions where the input variable is a complex variable. Okay, so this is the unit on calculus of functions of single complex variable. So we will start right from functions, then we will go to the limits, then continuity, then differentiability, then the derivatives and the rules of differentiation, and then we will switch to the integral calculus, okay, as we do usually in the real variable case. Okay, now as far as the real variable functions are concerned, we usually introduce ourselves to derivatives and integrals of single variable functions first, and then we go to multivariable functions. Okay, now just like we have functions of single variable in the real case, okay, we also have functions of real complex variables, okay, single complex variables. So this is what we are going to study in this section, okay, functions of a single complex variable. But later on you'll realize that to study the calculus of single variable functions where the function has a complex variable as the independent variable or the input variable, it is necessary to know the multivariable calculus of two real variables. Okay, we have already seen this in partial differentiation as far as the differential calculus is concerned. Okay, and we also do have functions with several complex variables. Okay, now this is the topic that is beyond the scope of this course. Okay, which one? The last one, the calculus of functions of more than one or at least two independent complex variables. Okay, so if we think of a matrix, then we already know this single variable functions where the variable is real, multivariable functions where the variables are real, the input variables and the output variables, and today we will be starting with this. Okay, functions and calculus of single complex variables. So the only thing that we will not study is this calculus or functions of several complex variables. Okay, so we'll start now. To begin with, we will start with revision of complex numbers, right from the definition, the representation, okay, and basic terms like modulus and argument, in particular principal argument. Okay, then we'll talk a bit about complex plane and those geometric objects which will be of interest to us, which are circles, then we have discs and annuli, or singular is annulus. Okay, so this is a ring shaped region, and we will also talk about what we call half planes. Okay, the definition is very easy to understand. Okay, and then we will introduce ourselves to a bit more complicated terms, okay, which may be new to you. We will call them open set and connected set. Okay, and when a set is both open and connected, we call it a domain. Alright, now these terms are there just for the sake of completeness, because when we define the limits, continuity and differentiability, we need them. Okay, but as far as problem solving is concerned, the terms aren't required. Okay, and then we will define a complex function in a way similar to the way we defined a real function. Okay, we will not follow the sets and relations approach, but we will define function as a rule which takes in a variable or a value and spits out another value. Okay, and then finally we will talk about graphs of a complex function, or in general the process of graphing a complex function. Okay, So this is a bit complicated process because we don't have the ability to visualize two input variables and two output variables. Okay, I mean, we have already seen this when we talked about functions of three variables. It was okay when we had functions of two variables, we reserved the third axis for the value of the function. Okay, so we could graph this as a surface in 3 dimensions. Okay, but when we went to functions of three variables, we found out that there is one axis that is lacking. All three axes are utilized for the input variables. Okay, so therefore we studied level surfaces just to get a feel of how the function is behaving. Okay, but as far as complex functions are concerned, we won't be doing anything of that sort. Okay, we will not talk about level surfaces, so to speak, but in fact we will make use of two different planes. Okay, the first plane is what we call the Z plane, which is the input plane, and the other one is what we call the W plane, the output plane. Okay, so this is what we will do in the first session. Now, people felt the need for defining new numbers because they were unable to solve equations of the kind x squared plus 1 equal to 0 in the set of real numbers. Okay, now this is how it is said, or it is believed, that the theory of complex numbers was developed. Okay, so we define a number root of -1, okay, and we call it I, and this number I has the property that when squared it gives us -1, and hence our problem of solving this equation is solved. But then I is a number which doesn't belong to the set of real numbers, and hence we extend our idea of real numbers to, or hence we extend the idea of numbers from real numbers to complex numbers, and usually the set of complex numbers is denoted by C. Okay, now you can also define complex numbers by an ordered pair. Okay, so you may define Z as an ordered pair A comma B. Okay, we usually write it as A plus IB. Okay, and when you define any complex number as an ordered pair AB, okay, then we need to define the rules or algebra of the complex numbers. Okay, now in particular we have to define the multiplication. Okay, because we can very easily add the numbers. Let us say if we have two complex numbers A1 B1 and A2 B2, then the addition is very simple. A1 plus A2 A1 plus A2 comma B1 plus B2. Okay, and so is subtraction. A1 minus A2 comma B1 minus B2. But when it comes to multiplication, this particular thing helps us. Okay, so this is how we actually define the multiplication, but when we treat it as a rule using ordered pairs, we just ignore it. Okay, so how do we define the product? If you have two complex numbers, let me write it here, A1 plus I B1 and A2 plus I B2, if we multiply them, okay, that is, if we are multiplying this complex number by the other complex number, we may even write it as the ordered pair A1 B1 multiplied by ordered pair A2 B2. Okay, so what's the result that we get? The result that we get is A1 A2 minus B1 B2, okay, plus I times A2 B1 plus A1 B2. So now you may realize that this result that we have got can still be treated as a complex number with ordered pair A1 A2 minus B1 B2 comma a2b1 plus a1b2. Okay, now it is the rule of addition and the rule of multiplication, which when remembered helps us in defining the whole structure of complex numbers, in particular the way we perform operations on the complex numbers. Okay, and then we have other terms. Okay, the first term is the absolute value of the complex number, so let me write it here now. Okay, or not? Okay, fine. Okay, so let's now go to other terms including modulus. Okay, so how do we define modulus of a complex number? Suppose the complex number is x plus iy. Okay, let's now switch to a more conventional notation. Mod of z or mod of x plus iy. This is given by root of x squared plus y squared. Okay, then we have the argument or amplitude. Okay, so let me directly go to the principal argument. So the a here is the uppercase a, and depending on the location of the complex number in the complex plane, or depending on the signs of x and y, the argument of z changes, but conventionally if it is in the first quadrant, meaning both are positive, this is how we define the argument. Okay, and then we have the last term, that is complex conjugate, which is x minus I. Okay, now with these rules we can or with the introduction of the complex conjugate, we can now even define the division of one complex number by the other complex number. However, it may still be noted that division by 0, which was undefined in the set of real numbers, is also undefined in the set of complex numbers. Okay, now let us go to the geometrical representation of the complex number. Okay, so this is what we call the complex plane or the z plane. The conventional x-axis, we were already calling it the real axis. Okay, this represents the real part of the complex number, which is a or x. Okay, so that is the real axis, and the imaginary axis is our y-axis, and the imaginary part, that is b, sits there. Okay, now I hope you might already be knowing this, but imaginary part of any complex number is a real number. Some students incorrectly say that the imaginary part is ib, but that is wrong. Okay, imaginary part is still a real number. Okay, and then to represent the complex number x plus iy, okay, or the ordered pair x comma y, we basically treat the real part to be the x coordinate of the point and the imaginary part to be the y coordinate of the point, and that's how every point on the complex plane represents or corresponds to a different complex number. Okay, now this representation of complex numbers in the form of ordered pair a comma b or x plus iy is the Cartesian form, but we also have polar form of a complex number. Okay, so in the polar form we need the two other things, okay, which were defined earlier. Which two? The modulus of the complex number and the argument of the complex number, generally the principal argument. Okay, now usually the mod is denoted by r and the argument is denoted by theta, it being an angle. Okay, you might already be knowing this. And then how do we find them? The r and theta, mod z is r, you already know the distance between the point P and the origin O, and theta is the angle made by the radius vector with the x-axis. Okay, and we let theta to be in the range minus pi less than theta less than or equal to pi for principal arguments. Okay, now we also have exponential form of complex number, right? So let me just tell you the formula and then we can go to the next part. Okay, so polar form of complex number is this: r into bracket cos theta plus I sine theta, where R is the modulus of the complex number defined by root of x squared plus y squared, and theta is the argument, usually the principal argument, but it can be in general any argument or principal argument plus or minus any integral multiple of 2 pi. Okay, now what is the exponential form? Exponential form of complex number is z equal to r into e to the power I theta, and this formula is due to Euler. Okay, in fact the connection between the exponential function e to the power x and the two trigonometric functions sin x and cos x, it comes from the exponential form of complex numbers and the Maclaurin series, okay, of cos, sin and e to the power x. Okay, all right, so the same two quantities, the modulus of the complex number and the argument of the complex number, they are used to define the exponential form as well as the polar form. Okay, all right, now this is a brief overview of what you already knew about complex numbers, but I think it is a necessary thing here to remind you that all of these things which you have studied in your 12th standard are important. And see, we may not be solving very high level problems based on this, but even if you understand the basics, it is enough to understand the calculus part, okay, starting from the functions. Now let us talk a bit about sets of complex numbers. Okay, fine. So I mean, we will talk about sets, but let's first define some terms, okay, and obtain their equations. We'll first talk about circles and disks. Okay, we'll start with the unit circle. Okay, now all of us know that the equation of unit circle is x squared plus y squared equal to 1. Okay, and if we are in the complex plane, okay, x squared plus y squared represents the square of the modulus of the complex number z. So the equation of unit circle in the complex plane is mod of z equal to 1. Basically we need to take the square root. Okay, and then if we use the center radius form of the circle in the complex plane, okay, and if we let the complex number a to have the real part h and imaginary part k, and the radius is, if the radius of the circle that we want is rho, okay, then in the Cartesian plane the equation is x minus h squared plus y minus k squared equal to rho squared, or the radius squared. Okay, applying the same logic, if we take the root, then this is going to be the modulus of the complex number x plus iy minus h plus ik. Okay, we know how to define the subtraction now, equal to rho, or this actually gives us mod of z minus a equal to rho. Okay, and as you can see here, the blue curve is actually the circle centered at a, whose real part is the x coordinate and the imaginary part is the y coordinate, and rho is the radius. Okay, so that is the circle C that we are talking about in the second point. Alright, now let's go to the third point. Here we are defining an open circular disk. Okay, from the equation it should be clear to you. The equation is, well, the inequality is mod of z minus a is less than rho. Okay, which is also the interior of our circle C, and this is what we call the rho neighborhood of A. Okay, now at this stage you have a new definition of neighborhood, in the sense that when we defined limits of a single variable function. Okay, even there we talked about delta neighborhood of real number a, but there we were interested only in the linear part. Okay, so suppose this is our real number a. Okay, real number a, then how did we define the delta neighborhood? The delta neighborhood of a was defined to be an open interval containing a, right, a minus delta comma a plus delta. Okay, so this is the delta neighborhood of a, deleted delta neighborhood of a, well, sorry, delta neighborhood of a. We are including a in it. But see, now this is an open interval, but because now we are in the complex plane, we are not defining open interval, we are defining open circular disk. Okay, so this is actually representing the interior of the circle, meaning the set of all those complex numbers whose distance from the complex number a is less than rho. Okay, and from the definition of open circular disk, the definition of closed circular disk follows. Okay, so it is mod of z minus a is less than or equal to rho. So this must be the union. In fact, it is the union. It is the union of the circle's boundary or circle itself and the interior of the circle. Okay, all right. Now exterior of the circle C should be very clear to you. Okay, exterior means that part which is neither inside the circle nor outside the circle. Sorry, let me define it again. The exterior of circle C is that part of the complex plane which is neither a part of the circle nor is a part of interior of the circle. Okay, so exterior is this, everything that is not either on the circle or inside the circle, that is the exterior of C. Okay, and if we consider two concentric circles, okay, centered at A but having different radii, rho1 and rho2, then we can define an open annulus. Look at the second figure. Open annulus means we are excluding the boundaries. Okay, so we are only interested in these numbers here. We will not be interested in the circles themselves. Okay, so this is an open annulus. Okay, and then closed annulus, the definition of closed annulus simply follows. Here we will include the interior of the circle 2 but exterior of circle 1, but at the same time we will also include the boundaries. Okay, so closed annulus is the set of all those points whose distance from A is less than or equal to rho2 but greater than or equal to rho1, and in open annulus we just don't include the equal to sign. Okay, now you may be already knowing this, but we will need all these things when we study the integral calculus of complex variable functions. Okay, all right, so now we have defined the circles and disks. Let's now go to half planes. Okay, so what are half planes? We already know what a plane is or what a planar surface is. Now half planes may be considered as follows. Okay, we'll first talk about open upper half plane. So let us first draw the complex plane. This is the real axis and this is the imaginary axis. Okay, now we define the open upper half plane to be the set of all those complex numbers in the z plane for which the imaginary part is 0. Okay, now the name upper comes from the fact that this particular region lies above the x-axis or above the real axis. Okay, and because it is an open plane, we don't include imaginary part equal to 0 line. Okay, that is the real axis or the x-axis. So open upper half plane is this. And similarly we can define the lower half plane. Yes, we may define it as an open lower half plane or closed lower half plane. remember, the moment we use the word closed, we have to include the equal to sign. Okay, so the lower half plane open, if we are considering the open set, then it is imaginary part of the z axis, imaginary part of the z or complex number z is less than 0. And if we are talking about closed lower half plane, then it must be imaginary part of the z less than or equal to 0. Okay, so let me now show open plane. So this includes both the both the third and the fourth quadrants. Okay, and on similar lines we can define the right half plane and the left half plane. Okay, suppose we are defining the right half. Okay, so the right half will be this one, open right half plane, the real part of z greater than 0. Okay, this one. And how can we define the left half, open left half plane? Let me use blue color once again. This is a planar surface, okay, wherein we take all complex numbers whose real part is negative. Okay, this one. So you may now think of quadrants. If it is an open upper half plane, then we need to include first and the second quadrants. Okay, if you are talking about lower half plane open, then third and fourth. If we are talking about open right half plane, then first and fourth. And if we are talking about an open left half plane, you have to include the second and the third. Okay, quadrants. So these are the half planes. Again, we will need them occasionally in the context of integral calculus, but we will need circles more frequently than half planes. Okay, and very rarely we may be in a situation wherein we will be required to consider ellipses. Very rarely. Okay, now usually when an ellipse appears, okay, its Cartesian equation is usually given. Okay, usually in most of the cases, even in the complex variable calculus. However, it is worth noting the equation of ellipse, in particular the definition of the ellipse based on the focus directrix property. Okay, so if we have f1 and f2 to be the complex numbers representing the two foci of the ellipse, then z minus f1's mod is the distance of the point z from the focus f1, and this is going to be the distance of the same point from the second focus f2, and we know that, well, sum of the focal distances of any ellipse is constant, which is equal to, in usual notations, 2a, length of the major axis. Well, this is still based on the focus directrix property, but here we have used the property that sum of focal distances is constant. Now what I'm saying is, it is essential to know these definitions, but you may not be required to use them in, well, it depends from problem to problem. Okay, and again, in particular, when we will study the integrals, all these things will come into play. Okay, yes. Now let us talk about sets in complex plane. All right. So we are going to start with definition 1, that is a point set S. Now the definition is very straightforward. The point set S is a collection of finitely many points or infinitely many points. Okay, so you may define S1 to be the set 2 plus 3i 4 minus 6i. That is still a point set. Okay, collection of finitely many points. And if you define another set S2 to be the set of all those complex numbers z such that their real part is positive. Okay, we've already seen this in the half plane. This is another point set. Okay, let us now go to open set, analogous to open interval. Okay, in the real variables. So an open set is a set of points or a point set such that every point has a neighborhood consisting entirely of points in S. So examples of open set, well, S2 is an open set, and we can also define S3 as the set of all those points z such that mod of z minus a is less than rho. Okay, so this is still an open set. Now let's go to boundary point. Now a boundary point is that point such that every neighborhood of z consists of points in S and points not in S. Now this is important. For this, let us draw a circle centered at A, okay, the complex number A, and let's focus on the boundaries. Okay, if this is a boundary point, then no matter how small the radius is or delta is, okay, that particular set is going to consist of points which not only belong to the circle or the interior, but also the points which belong to the exterior. Okay, so this is called as a boundary point Z, okay, or a boundary point of a set S. Okay, so all boundary points are in the example that we are discussing in this set. Okay, all right. Now let us go to connected set. So a connected set is such that any 2 points in that can be joined by a chain of finitely many straight line segments lying on it. Okay, so clearly circle's interior is a connected set. Okay, so let me now tell you an example of a set which is not connected. S1 is not a connected set because S1 consists of only 2 points, okay, which are not coincident. Okay, so if we decide to start from 2 plus 3i and reach 4 minus 6i, the very first step is going to be it will consist of a point which doesn't belong to S1, so this is not a connected set. Okay, now you may think that annulus is also not a connected set, but you can still let's say you start from this point, okay, and you would like to reach here. Although this straight line part doesn't belong to that, you may consider this path. Okay, now we have reached the second point starting from the first point through finitely many line segments. Yes, okay, so this is still a connected set. Okay, finitely many straight line segments lying on S. Alright, now let's go to domain. Domain is perhaps the most important term here. Okay, so a domain is a set which has to be open and it has to be connected. Okay, now if you understand the definitions of open set and connected set, then you will immediately realize what we call domain in this particular branch of mathematics. Okay, so you may come up with sets which are open but which are not connected, sets which are both open and connected, sets which are not open but connected, and sets which are neither open nor connected. So basically 4 possibilities, only one of them is going to consist of domains. Alright, Fine. Then let's talk about complement. You already know this from your set theory. Okay, so complement of any set S, any point set S, is the set of points in the complex plane which do not belong to S. And as a consequence of the definition, if S is open, then S complement must be closed. For example, let's consider S3. Okay, and let's say our job is to find out its complement S3 prime or S3C. So this is going to consist of all those complex numbers such that mod of Z minus A is greater than or equal to rho. Okay, so basically S union S complement should be C and S intersection S complement must be a null set. Okay, so starting with the easiest definition of a point set, we have seen what an open set is, analogous to open interval. Then we have defined the boundary point Z. Okay, and you may now see that this has some connection with equations of curves. Okay, let us say circle. Then we have seen connected sets, and the idea of connected sets is important to define domain. Okay, so domain is any open and connected set. And finally we have defined complement of a set, which is very easy. And these rules that I have listed, you already know them from the set theory in your 11th and 12th standard calculus. Okay, S union S complement is the set of complex numbers. There you called it universal set, so here the universal set is the set of complex numbers itself. Okay, and of course the intersection of any set and its complement should be a null set. Okay, and it goes without saying that if S is open, then S complement must be closed, and if S is closed, then S complement must be open. Okay, all right. So let us now go to complex functions. Now, as I told you in the introduction part, we are not going to adopt the Cartesian product and relation approach here. Okay, so this is how we define a complex function. So a complex function f, we are still going to use the f notation. Okay, so a complex function f is a rule defined on set S, which is the subset of the complex numbers. Okay, which assigns one or more, so I'll explain you this later, which assigns one or more complex numbers w for every z in that particular set S. Okay, now when we defined real functions, we did not consider multi-valued functions. Alright, meaning we did not want x, okay, the real number x, to have two different images, image 1 and image 2. In particular, if we consider the function root of x, okay, for positive, okay, let's consider positive values. Okay, you know that there are two possibilities. For example, if we go to root 4, we may have 2 or minus 2. Okay, so root x is multi-valued, but we ignored this and we made it single valued. Okay, so in complex functions we kind of remove that restriction of functions being single valued, and we say that a function f is a rule defined on any set S, okay, which may assign a single complex number or multiple complex numbers w for every point z in that particular set. Okay, so naturally S is going to be the domain of this particular function. Okay, Again, although I explained you what multi-valued functions might be, we will not be considering them, okay, as far as our calculus problems are concerned. Alright, now it is important to understand, for a function, it being a rule and it takes in a complex number and produces another complex number, okay, and if the output variable is w, it is also going to have two parts, okay, the real part u and the imaginary part v. So this is the convention, okay, if z is x plus I y, okay, then w, which is f of z or f of x plus I y, is now u plus iv, and both u and v are functions in their most general sense of x and y, okay. Now you may realize that the output that we are going to get consists of two functions u and v, and both are multivariable functions. So knowing the calculus of multivariable functions is going to help us, okay. Now let me tell you some examples. We are first going to start with example 1, which is known as complex exponential function. Okay, so we already knew the real exponential functions, right, e to the power x, okay. So now we are defining it in this way, e to the power z, where z is the complex number x plus I y, okay, this is the real part, and well, you can use the Euler's formula now. E to the power I theta is cos theta plus I sin theta, okay. So if we were to find the u and v, or the real and the imaginary part of the complex exponential function, then u, the real part, would be e to the power x cos y, and the imaginary part would be e to the power x sin y. A pretty straightforward evaluation, okay. Then we can define the trigonometric functions sin z and cos z, and here the input is not a real number, okay, so we cannot really call z to be the angle here, okay. So sin of z is 1 upon 2i e to the power iz minus e to the power minus iz, and cos of z is 1 upon 2 into e to the power iz plus e to the power minus I z. Now these definitions will not be very difficult for you if you already know the alternate definition of cos theta and sin theta using Euler's formula, e to the power I theta plus e to the power minus I theta by 2, okay. So if you use cos theta plus I sin theta and cos theta minus I sin theta terms go, you get 2 cos theta in the numerator, and then you divide it by 2 so that you get cos theta. Okay, so what we are doing here is to define the complex cosine function cos of z. We are just replacing theta by z and allowing it to be any complex number, okay. Same thing with sin z, okay. So for sin theta we have e to the power I theta minus e to the power minus I theta, which gives us 2i sin theta in the numerator, so you have to divide it by 2i to get sin theta, okay. So if you replace theta by z, then you are going to get the complex sine function, okay. On similar lines, we can define hyperbolic cosine function for a complex variable z, cos h of z and sin h of z, okay. Now again, these definitions follow from the real counterparts, okay. So if we have cos h of theta, then it is e to the power theta plus e to the power minus theta upon 2, and sin h of theta as e to the power theta minus e to the power minus theta, you don't have I there, upon 2. Okay, so when you replace theta by z, you will get both circular functions and hyperbolic functions. Okay, all right. Now the fourth function is a bit interesting, log of z. Now you may observe that here the first letter of the log ln, that is L, is uppercase, and so is the argument. Okay, now this is where the idea of multi-valued function comes into play. Okay, so let us try to define logarithm of a complex number z, and then we will go to the principal value. Okay, we know that z is x plus iy. So if we are defining log of z as simply log of x plus y, then it is not going to help us anymore, or it is not going to provide any information as far as the evaluation is concerned. Okay, so what we will do is we will make use of the polar form. Okay, in particular the exponential form. Okay, sorry, not the polar form, exponential form. Okay, so log of e to the power I theta into r. Okay, now this immediately allows us to use the property of logarithms. Log of a into b is log a plus log b, and eventually log r plus I theta, because the base of the logarithm is e itself. Okay, now you know that the argument of any complex number is a multi-valued function. Okay, meaning if phi is the argument of that complex number, then any number in the form phi plus or minus 2 pi n is the argument. Okay, so this is the reason why we say that logarithm is a multi-valued function. For example, suppose we consider the complex number 1 plus root 3i. Okay, and suppose we are interested in finding the logarithm of this. We know that the modulus of this complex number is 1, isn't it? Or not 1? Okay, I think it is 2. Yeah, it is 2. Okay, argument is 2. Sorry, modulus is 2. Okay, root of 1 squared plus root 3 squared. Yes. Okay, so this is the real part. Now when we go to the imaginary part, okay, I into, we can have tan inverse of root 3. Yes, but at the same time we can also have plus 2 pi plus 4 pi, or in general plus 2n pi, where n is any integer. Yes, and therefore we will get multiple values for logarithm of 1 plus root 3i, don't we? The first value is log of 2 plus I times pi by 3. Okay, but we may also take it as log of 2 plus I times pi by 3 plus 2 pi. Okay, one of the other values. Now from the equality of complex numbers, we know that these two numbers are not equal because their imaginary parts are not equal. But still, both are what you have got as the output complex numbers when you input 1 plus root 3i in the logarithmic function. Okay, so this is why we say that complex functions may be single valued or may be multi-valued. Okay, but as of now we will consider only the single valued functions, and hence we will consider the principal argument. Okay, meaning when we talk about principal logarithm of 1 plus root 3i, the real part is not going to change, but for the imaginary part we'll only consider the principal argument. Okay, or that argument or that angle theta which lies in the interval open at minus pi, closed at pi. Okay, so this is the idea behind complex multi-valued functions. Okay, we have seen 4 of them. Well, not 4, in fact 8, right? 6 of them. Okay, the complex exponential function, the trigonometric functions cos z, sin z, then hyperbolic functions cos h of z and sin h of z, and the logarithmic functions. Okay, so the logarithmic function is telling us that the real part is the argument, well, logarithm of the modulus of the complex number, okay? And the imaginary part is actually the argument, okay, or v. Now note that both log of mod z, which is 1 upon 2 log of x squared plus y squared, and argument of z, generally tan inverse of y upon x, both are functions of two variables, okay? Sticking to the definition that w consists of two functions, both multivariable functions, in particular two variable functions. The real part is u, common notation, the imaginary part is v. Now we'll answer the final question, how to graph a complex function, okay? In the introduction I said that it is not as easy at it as it may look, okay? Graphs of complex function. So let us now go to that. Point 1, you cannot plot a graph of complex function in 3 dimensions, okay, because you have two input variables xy and two output variables u and v, okay? So this is clearly an impossible task in 3 dimensions, although some softwares use color schemes to include the fourth one, okay, which otherwise cannot be incorporated, okay? So meaning you may have x and y, and let's say the real part as u, and for imaginary part they use some color, okay? So you may have seen surfaces when we studied partial differentiation or graphs of two variable functions, but that surface was a single colored surface, but now that surface itself is might be a colored surface, and the color signifies the imaginary part, okay? Or sometimes the argument is the color and the modulus is the z coordinate, okay? So it depends, but otherwise depicting the function w is an impossible task in 3 dimensions. All right, but what we do is usually we take two planes, okay? We call the first plane to be the z plane, in which the input values are there, so domain is a subset of C, the input plane, but we consider yet another plane, okay, and we call it a w plane, okay? So graphing the functions, the complex functions requires you to have the z plane and the w plane. For example, suppose we are studying the function z squared, okay? So entire imaginary axis, okay, this one, it goes without saying that this will get mapped to the negative real axis, right? Because I squared is -1 and squares of all purely imaginary numbers are negative real numbers, okay? And 0 is square, it's 0. Okay, so any point here on the imaginary axis gets mapped to the negative real axis if the function is f of z equal to z squared, okay? So at a time we can think of what happens to a point or a line or in general any curve, okay? But we cannot consider the entire z plane because it is the domain of the function z squared, and we may not get a good idea of what's happening to that. But if we consider blocks, usually squares or grids, we can think of how the squares get distorted or the shape of the squares getting changed when they are mapped to the w plane, okay? Now this is for the very simple cases of case of z squared, okay? The trivial case f of z equal to z is not very much interesting, right? All right, so let us now discuss few more things about the function z squared. Look at these two figures. The figure on the left is the z plane and the figure on the right is the w plane. Okay, now on the z plane you can see a grid. Okay, the blue lines represent complex numbers with constant imaginary part. Okay, so let us say these are the complex numbers in the form x plus ai, where a is any real number. And if you decide to square, what will you get? You will get x squared minus a squared plus I times 2ax. Okay, and depending on, so this is the u axis now. Okay, so x squared minus a squared is going to sit here, all right, and 2ax will sit here, the v axis. Okay, now if you manage to connect u and v, you will get the equation. Okay, now these are looking like parabolas. Okay, and then you can just think of the distorted line. Okay, now let us talk about the orange lines. Now orange lines are those lines which have constant real part. Okay, so you may think of these lines as b plus iy. So if you square, okay, b is any real number, if you square them, then you will get b squared minus y squared as the real part and 2by as the imaginary part. Okay, so 2by sits here and b squared minus y squared is to be considered on the u axis. So again, if you start mapping or start to find a relation between u and v here, you'll get curves. Okay, alright, so depending on the squares that you have here, you may think of their distorted versions on the w plane, and this is how usually the graphs are plotted. Okay, you definitely cannot do that for the entire real axis, entire the complex plane, but you may consider a part of the complex plane or the domain of the function and see what's happening to the complex numbers. Okay, in particular to their real and imaginary parts. Okay, now it is interesting to note that the entire real axis, okay, let me use blue color, the entire real axis here, okay, will be mapped on the u axis, or in fact the positive u axis itself, as we discussed. Okay, square of any real number is always a real number which is either positive or 0, and if we consider the imaginary part or the y-axis here, okay, then this will get mapped to the negative u-axis. Okay, yes, and then maybe you can take a as 1 and b as 1 and see what equations you get in the uv plane. Okay, that will give you some idea as far as the function z squared behavior is concerned. Okay, now like this you can go to z cube or log of z or sine z and so on. Okay, just to understand the behaviors of functions when the input variable is a complex variable. Okay, fine. So this was the introduction, and in particular how the functions are defined in the complex plane and how we build the graphs.